For the first topic of this chapter, I will be discussing single sideband signals. In amplitude modulation, two-thirds of the transmitted power is in the carrier, which itself conveys no information. The real information is contained within the sidebands. One way to improve the efficiency of amplitude modulation is to suppress the carrier and eliminate one sideband. The result is a single sideband signal. The first step in generating an SSB signal is to suppress the carrier, leaving the upper and lower sidebands. This type of signal is referred to as a double sideband suppressed carrier signal. Note that double sideband suppressed carrier modulation is simply a special case of AM with no carrier. A typical DSB signal is shown. This signal, the algebraic sum of the two sinusoidal sidebands, is the signal produced when a carrier is modulated by a single tone sine wave information signal. The carrier is suppressed, and the time domain DSB signal is a sine wave at the carrier frequency, varying in amplitude as shown. Note that the envelope of this waveform is not the same as that of the modulating signal, as it is in a pure AM signal with carrier. A unique characteristic of the DSB signal is the phase transitions that occur at the lower amplitude portions of the wave. In the time domain on the left, note that there are two adjacent positive going half cycles at the null points in the wave. That is one way to tell from an oscilloscope display whether the signal shown is a true DSB signal. A frequency domain display of a DSB signal is given on the right. As shown, the spectrum space occupied by a DSB signal is the same as that for a conventional AM signal. Double sideband suppressed carrier signals are generated by a circuit called a balance modulator. The purpose of the balance modulator is to produce the sum and difference frequencies, but to cancel or balance out the carrier signal at the output. Here is an example of a balance ring modulator, sometimes called a balance lattice modulator. The operation of the lattice modulator is relatively simple. The carrier sine wave, which is usually considerably higher in frequency and amplitude than the modulating signal, is used as a source of forward and reverse bias for the diodes. The carrier turns the diodes on and off at a high rate of speed, and the diodes act as switches that connect the modulating signal at the secondary of T1 to the primary of T2. The current in the upper part of the winding produces a magnetic field that is equal and opposite to the magnetic field produced by the current in the lower half of the secondary. The magnetic field thus cancel each other out. No output is induced in the secondary, and the carrier is effectively suppressed. When the carrier polarity reverses, D1 and D2 cut off, and D3 and D4 conduct. The result is a 180-degree phase reversal. With this connection, if the modulating signal is positive, the output will be negative and vice versa.